So before we talk about ethical issues, let's first watch a few short videos.
Is there supposed to be some audio?
Okay, so you can see my slides, right? Okay, good. So let's start from the very old and classic trolley problem. So there's a runaway trolley barreling down the railway tracks. Ahead on the tracks, there are 5 people tied up and unable to move. The trolley is heading straight for them. You are standing some distance off in the train yard next to a lever. If you pull this lever, the trolley will switch to a different set of tracks. However, you notice that there is one person on the side track. You have 2 options: do nothing and allow the trolley to kill the 5 people on the main track, or pull the lever, diverting the trolley onto the side track where it will kill one person. What's the right thing to do? So there are many variants. One is the fat man variant. So a trolley is hurtling down a track towards 5 people. You're on a bridge under which it will pass. And you can stop it by putting something very heavy in front of it. As it happens, there is a very fat man next to you. So your only way to stop the trolley is to push him over the bridge and onto the track, killing him to save 5. The fat villain, where the fat man is the villain who put these 5 people in peril. The loop. So the loop is when the trolley problem with a variation where you you have a track towards 5 people, and you can divert it into a second track, which later rejoins the main track. So diverting the trolley still leaves it on the track, which leads to the 5 people. But the person on the side track, this red person, is a fat person who, when he's killed by the trolley, will stop it from continuing on to the 5 people, which is here. This is the 5 people. So it looks very similar to the trolley problem, original one, but here the death of the 1 actually is part of the plan to save the 5. So if we fail to act, then we'll effectively be allowing the 5 to become a means to save the 1. There are some slight variations. And also the man in the yard. So you can divert the trolley by colliding another trolley into it. But if you do, both will be derailed and go down a hill and into a yard where the man is sleeping in a hammock. So he will be killed. So philosophers have discussed many variants of the trolley problem since 1967, the original version. So here's one version with probabilities. So you're in a situation where if you kill a pedestrian with probability 1, but it's not your fault. So here's a jaywalker walking right into the highway. So if you drive straight ahead, you will kill the jaywalker, but it's not your fault. But if you kill a different person, pedestrian, with probability P, and it is your fault. So the pedestrian is on the sidewalk. So if you turn into him, then it is your fault. So what's your threshold for choosing the value P threshold for making the choice? Obviously, if P is equal to 0, then you choose B because you're not going to kill anyone by turning to the side. If P is equal to 1, you choose A because you're going to kill the pedestrian on the sidewalk with probability 100, but it's your fault. So you'll never do it. You just kill the jaywalker where it's not your fault. But what is the threshold for making the decision? If P greater than or equal to the P threshold, you choose A, otherwise you choose B. So that's an interesting question, right? So you have 2 extremes with clear answers, but not so clear for a intermediate P threshold. So see, many people are very quiet. So let me try to ask someone. Alexander, are you there? Alexander? Leon? No?
Yeah, I'm here.
So what's your P threshold?
It's a very hard question. I'm not sure actually. Let me think about it.
Yeah, so I just wanted to see if anyone is actually there, or you just walked away.
I'm here. Yeah, I
That's
just
fine.
couldn't find the unmute button first, but I don't know. It's really hard question to put a number on.
Yeah, so that is a hard question. The point is not to make everyone choose a value. It's just a thought experiment.
Yeah.
But that is actually not realistic because how do you get the P, right? I mean, it's not possible or very difficult to calculate a P for killing a person. So, yeah. So that's the MIT moral machine experiment mentioned in the video. It's a 2016 survey indicating that people wanted an autonomous vehicle to protect pedestrians, even if it meant sacrificing its passengers. But the survey in 2016 also indicated that they won't buy self-driving vehicles programmed to act this way. So morally, people say, okay, if the AV kills the passenger, but saves 20 children who are pedestrians, then it should do it. But when they're making the purchase decisions, they won't buy such a vehicle because they are the passenger. So this particular survey prompted the MIT moral machine experiment, a platform for gathering a human perspective on moral decisions made by machine intelligence, such as AVs. So here's the simple setup. A AV must choose between killing 2 passengers. Here, 2 or 5 passengers. Oh, okay. So the figure is not very. Oh, okay, 2 passenger. Here it draws 3 or 5 pedestrians. Here it draws 3 pedestrians. So AV experiences a sudden brake failure. Staying on course would result in the death of 2 elderly men and an elderly woman who are crossing on a do not cross signal. So they are jaywalking. Swerving would result in death of the 3 pedestrians because they hit a barrier. So adult man, adult woman, and a boy. So you can also design other scenarios by yourself. So accident scenarios are generated with 9 factors: sparing humans versus pets, staying on course versus swerving, sparing passengers versus pedestrians, sparing more lives versus fewer lives, sparing men versus women, sparing the young versus the elderly, sparing pedestrians who cross legally versus jaywalking, sparing the fit versus the less fit, and sparing those with higher social status versus a lower social status. That is the rich guy versus homeless person. So the platform generated 40 million decisions, got 40 million responses in 10 languages from millions of people in 233 continents. So here are the analysis. So preference in favor of the choice on the right side. So here's the bunch of choices. On the left side, here's a bunch on the right side. So delta P on the horizontal axis is the difference between the probability of sparing characters possessing the attribute on the right and the probability of sparing characters possessing the attribute on the left. So for example, for the attribute age, elderly versus young, it's 0.49. 0.49 here. So the probability of sparing the young character is 49% greater than the probability of, I'm sorry, it's not 49%, it's 0.49%. No? No, it is 49%. Yeah. Standard deviation, standard error is this much. So it's very sharp distribution. So generally, people prefer to spare the young than the old elderly. They prefer to spare more characters than the fewer characters. Yeah, and prefer to save females than males, and so on. So if you normalize the preferences to adult man or woman, if you set them as 0 and graph the other preferences, you have the curve on the right. So generally, stroller with a baby, a girl, boy, they are preferred to adult man or woman, and dog, criminal, cat, old man, they are less preferred compared to a normal adult man or woman. And there are cultural clusters. So as mentioned in the video, you have the Western cluster, which is Europe, North America. I think it's Argentina here, Australia. And you have the Eastern cluster, which is Asia, Middle East countries. And you have the Southern cluster, which is South America and part of North Africa. Yeah, French and French colonies. So the preference to spare younger characters is much less pronounced for countries in the Eastern cluster, much higher for countries in the Southern cluster. So Eastern culture respects the elder more than Western culture. Same is true for preference for sparing higher status characters. So countries in the southern cluster exhibit a much weaker preference for sparing humans over pets. So I guess they like animals. Weaker preference for sparing pedestrians over passengers. And the moderate preference for sparing the lawful over the unlawful appear to be shared to some extent in all clusters. Lawful means that a regular person, unlawful means a criminal. So that's the preference chart for the three clusters for different preferences. Yeah. So that's an interesting study. It's a very large scale survey, but is it really worth the time? So many philosophers argue about it, but technologists do not. So many argue that ethical issues are just a distraction from the real problem of AV safety and security, especially in the presence of machine learning, deep learning algorithms. None of the AV accidents in recent years involved any ethical decisions similar to the trolley problem. They are due to failures in sensors or perception algorithms. Sebastian Thrun, the former head of Google's self-driving car project, former professor at Stanford University who led the development of Stanley, a winner of the DARPA Grand Challenge in 2005. He has an interesting quote that said, I think it's a great thing for philosophers to discuss these kind of problems they can get tenure at their universities, but it's not of practical relevance. If we manage with a certain car technology to halve the traffic deaths in the world, which means that if we are able to have 500,000 fewer deaths in total, then for this extremely rare, purely hypothetical trolley problem that might occur once in 100 years, I think whatever the outcome is, the mental energy that philosophers have spent on discussing it is completely out of proportion to the benefit of others on one problem. I will leave it at that. So that's the status of AV ethics. It has a lot of literature in the social science, philosophy areas, but in the technology area, in all the people who are really engineers who are developing self-driving technology, they generally dismiss it as something that's unimportant. So here's the AV testing legislation status in the United States. So United States has 50 states with a lot of autonomy. So there's no federal regulation for regulating testing of AVs. Instead, each state has its own legislation. So first of all, it's absolutely necessary to test AVs on public roads for technology development. If you test it in the simulator, the simulation is not, it cannot be 100% accurate. There are always inaccuracies. If you test it in a testing ground, like in many places, they set up testing grounds with street signs and fake pedestrians and fake houses and everything. Still, the traffic scenario is not realistic. You need to go into the real world and go into a busy intersection and test in that difficult scenario for the AVs. So testing on public roads is necessary, but is it ethical? So several states have no proposed legislation, but other states like Nevada, California, Texas, and Arizona, they are hotbeds for testing AVs. So if you notice these similarities among the states, right? Nevada, California, Texas, they are all southern states with sunny weather, right? It's not Michigan. It's not, in the northern part of the United States, because AVs have difficulty handling snow. So yeah, for the sunny parts, it's safer to test AVs on the road. So for the this testing issue, my opinion is that yes, but if human operators are alert and responsible, but is it realistic? For the accident that killed a pedestrian by Uber's vehicle, so the testing human operator was not paying attention. And it's difficult to pay attention, right? If the car drives 99% of the time very well without human intervention, and only once in a day or once in a few days it needs intervention, then it's hard for the human to pay attention. So okay, so that's the part on AV ethics. Any questions? Let me see the. Oh, I see something. So someone is asking, can we choose to stop the vehicle? Is there any threshold value to make the vehicle stop? Oh, so it's the trolley problem with a threshold. So the assumption is that the vehicle is too fast to stop, for example, on the highway. So if you can stop, obviously that's a option that saves both people. But for example, in the Uber accident, the pedestrian came out of the darkness, and the vehicle really cannot possibly stop at such a short distance. So in that case, the only way to prevent the collision is to swerve to the side. And then you have two choices only, yeah. So stopping distance is actually quite long on the highway. I think, I don't know. So it's like quite 50 meters or something. So it's really hard to stop. So let's move to V2X section, which is the last section of the introduction chapter. So V2X means vehicle to everything. So vehicle to vehicle, vehicle to infrastructure, to the traffic signs, traffic posts, vehicle to pedestrian, which really means to pedestrian's mobile phone, vehicle to network, which is essentially to the cloud. So vehicle to vehicle, so in the 3GPP standard, which is a telecom standard, it defined 4 types of V2X applications. V2V is collision avoidance. For collision avoidance, one type of application for V2V. So for example, if you're turning and you cannot see the vehicle across the corner, then V2X can help you avoid a collision. A vehicle to pedestrian can help issue safety alerts to pedestrians and cyclists to their mobile phones. Vehicle to infrastructure so it's adaptive traffic light control, traffic light optimal speed advisory. So we saw one example of University of Michigan attack on V2X communication, where the infrastructure traffic light is adaptive instead of on a fixed schedule. Speed advisory is when when the light is green all the way, then you may get a message in your car that says you can go faster. If it's red, it'll tell you beforehand, so you can slow down beforehand. So vehicle to network is vehicle to the cloud. So it's for traffic routing, real-time traffic routing, and cloud services. So V2X communication is divided into 2 camps. One is DSRC. So it's based on essentially Wi-Fi, a variant of Wi-Fi. 802.11p at 5.9 gigahertz. So I forgot to put in the what DSRC means. It's distributed short range communication. So it's Toyota and General Motors are in this camp. So it's for latency sensitive applications because connection is local. It's a local Wi-Fi connection between 2 vehicles. So it's used in wave wireless access in the vehicular environment, or IPv6. So the other camp is cellular V2X. Representative companies are Qualcomm and Ford. So traditionally for latency tolerant applications, such as over-the-air updates, where you download a patch from the connection. So cellular V2X typically requires a base station. So just like your mobile phone connection, when you are on the road, you can only use cellular connection. But when you're at home or in your office, you can connect to the Wi-Fi. So that's exactly the same here. So DSRC is Wi-Fi, CV2X is cellular. So so that's the traditional wisdom. DSRC is for latency sensitive applications, and cellular V2X is for latency tolerant applications. But with the advent of 5G, CV2X seems to be winning. So it seems to be gaining ground, becoming more prevalent, used also for latency sensitive applications. So I developed the slides based on Qualcomm's CV2X approach. So CV2X is the only V2X technology with a clear evolution path to 5G. It's backward-forward compatible. So CV2X release 14 had a strong evolution to 5G NR-based CV2X, which augment release 14 with complementary as well as new capabilities while maintaining backward compatibility and so on and so on. So okay, so you can read it yourself. So V2X application scenarios. So one is non-line of sight sensing. So the sensors we discussed, camera, LiDAR, radar, ultrasonic, they're all line of sight sensors. That is, if there's a building or a barrier that obstructs your field of view, then the sensor is blinded. So V2X can help get around that. It provides 360 degrees awareness, works at night and in bad weather conditions. So obviously it's not affected by the lighting condition. So if you have a blind intersection with vulnerable road users, VRU refers to pedestrian or cyclists. So suppose there's a tall building here and the cars can't see each other. I can't see the VRUs. Then all the sensors we discussed won't help. But V2X will help you to detect these objects. Conveying intent. So this is when it shares intent, sensor data, and path planning information for higher level of predictability. So say this vehicle sees a road hazard and it does a sudden lane change. So it may communicate with the vehicle behind with a V2X message to alert the blue vehicle so that it can change lane earlier. Situation awareness. So this is when the offers increased electronic horizon, so to issue soft safety alerts and graduated warning. So if there's a congested section of road ahead, so the congestion information, the queue warning can be sent to the vehicles behind to so-called shockwave damping. So that is the vehicles, the traffic can form a shockwave in case of congestion. So shockwave damping essentially tries to warn the vehicles ahead of the congested section so that they can maybe take a different path to avoid the congestion. So it damps the shock wave, relieves the congestion. So so these two scenarios are V2X has the benefit of long distance communication. So maybe a few miles ahead of the congestion or the road hazard, the vehicle can get a warning. Whereas with sensors, it's only sensing range is only a few hundred meters. So that's a limitation for sensing. So V2X evolution. So the V2X based on L2.11p or CV2X R14 is mainly for basic safety. So that's the SRC Wi-Fi connection. So it can transmit only very short messages, very simple messages due to the limited transmission bandwidth. For enhanced safety, the range is increased and reliability is increased for CV2X release 14 and 15. For advanced safety, release 16, then you have higher throughput, higher reliability, wideband ranging and positioning, lower latency. So that's the evolution path. So evolution towards 5G. So from the basic communication with R12 and 13 to the enhanced safety with enhanced communication range and reliability to autonomous driving with CV2X R16 for advanced safety applications. So network independent, it means that if it involves the base station. So if it's network dependent, it means that you have to connect to the base station and then connect to the other vehicle. It incurs a long latency. But if it's network independent, then the vehicles communicate peer-to-peer without a base station in the middle. Communication can be broadcast or unicast plus broadcast. So high-speed support, high-density support, throughput for 5G, it'll be ultra-high throughput. Latency will be ultra-low latency. Reliability will be ultra-high reliability. Positioning will be a wideband ranging and positioning. Positioning means localization. So 5G will essentially be a revolution in wireless communication. It'll essentially change the paradigm. So in the presence of 5G, when 5G is realized, people have proposed a so-called remote control paradigm where the autonomous vehicles are connected to a central control room with lots of operators. Whenever the AV encounters a difficult situation like a construction zone with lots of pedestrians and it's confused, it will ask for help from humans in the control room. And control room operator can steer the vehicle out of the difficult situation. And then the vehicle can drive autonomously again. So that relies on 5G. If it's a current or cellular connection, it's not going to work. The reliability is too bad. But for vehicle remote control, you have to have 5G. So yeah, that's the communication mode, transmission mode. One mode is network communication. One is direct communication. Network communication requires a middle base station and direct communication, including V2I infrastructure, V2V, V2P pedestrian, they're point to point. There's no need of the cellular network connection. So it's has much lower latency and higher reliability. So latency tolerant use cases. This is where the latency does not matter very much. One is to discover parking and charging stations. One is traffic flow queue warning. So the front vehicle sends a warning message to the rear vehicle that there's a congestion ahead. One is a cloud-based sensor sharing. So maybe one vehicle has a powerful sensor, the other vehicle can share its view. Maybe you can project the your friend's vehicle's camera image to your own vehicle, so that your vehicle can see far ahead. And road hazard warning, 1 kilometer ahead. So here's one vehicle stranded, broken down on the road, and and it's at a turning corner point, so it's easy to hit the car. So you can get a warning 1 kilometers ahead. So all these use cases are not latency critical. So for direct communication, these are latency critical applications, especially for non-line of sight scenarios. One is a do not pass warning. So on this 2-lane road, if you pass a vehicle, you need to go to the opposite lane. But if it's an oncoming vehicle on this lane, then it can be dangerous, especially if there's a corner. So this allows the vehicle to get a warning, so do not pass right now. Blind curve, local hazard warning. So you may have a parked, broken down vehicle here, and you may get a warning a long distance from the broken down vehicle. Roadworks warning. So this is when you have a road construction and the truck is blocking the view of the rear vehicle, so the rear vehicle cannot see it and may run into the obstacle when the truck swerves. Intersection movement assist at a blind intersection. So this is when you have tall buildings in the middle, so the cars cannot see each other. And you can use the V2X to warn the two vehicles. In this case, to warn that there's an emergency vehicle which may be running the red light. So vulnerable road user alerts. So the vulnerable road user, a pedestrian or a cyclist, is carrying a mobile phone with the app installed. In this case, when it's crossing the road, the vehicle can get a warning that there's a VRU in the road. Left turn assist, so it can help judge the distance of the oncoming vehicle and advise the if it's time, if there's enough space and time to make the left turn. So direct communication, these usage scenarios do not require USIM. So a SIM card is the little card in your mobile phone. That's for cellular connection to the network. But for these scenarios, direct communication, you don't need that SIM card. Autonomous resource selection. So this is a wireless bandwidth resource selection. The car selects resources without network assistance. GNSS time synchronization. So CV2X can use GNSS for synchronizing time without relying on cellular networks. So self-managed versus network-assisted. So self-managed is direct communication with no cellular network connection, and network-assisted requires a assistance from the network. So direct connection, direct self-managed has reduced cost. Do not use licensed spectrum for control, increased reliability, and reduced complexity. So do not rely on cooperation between operators for resource assignment. Does not require a subscription. So here's the bandwidth assignment. ITS is Intelligent Transportation System. So it added the CV2X support in ITS spectrum. So in this 10 megahertz spectrum, messages of it supports today's safety use cases on small subset of the band. Use 802.11p, which is Wi-Fi, or cellular V2X. Then on this 70 megahertz band spectrum, you have advanced safety 5G V2X services. So supports advanced safety services with higher bandwidth sensor sharing and wideband ranging positioning. These can CV2X and 802.11 can coexist by being placed on different channels on the ITS band. So even though 802.11p and CV2X are sharing the same spectrum, they can still coexist due to different channels. But this 10 megahertz is only for basic safety services due to limited bandwidth. The 70 megahertz here has much higher bandwidth. I saw this demo where a vehicle driving behind another vehicle, maybe a few kilometers apart. The behind vehicle can see a video stream captured by the camera of the front vehicle, assuming that, of course, the front vehicle gives it permission. So that's a very interesting usage scenario where you can see a mile ahead. So CV2X in the ITS software stack, so it essentially it's a plugin replacement for existing protocols. So you can reuse the established service and application layers defined by automotive and standard communities. And then you can develop abstractions to interface with 3GPP lower layers. Reuse of the security and transport layers. And so essentially you plug in this lower part and all the upper part can stay the same. So deployment of CV2X is a combined roadside unit RSUs and 4G, 5G small cell, benefiting from cellular network densification. So the green parts are small cells. Yeah, that's the 4G, 5G small cells. And the purple parts are the RSU roadside units. So in this case, it's placed co-located with traffic lights. In the traffic posts, you often see boxes with a sign that says telecommunication equipment inside. So that's where you place the RSUs. So in 5G, I don't know if you know about 5G. In the 3G networks, the base stations are very sparse. So you may have a area several tens of square kilometers area with one base station. But for 5G, it'll be very dense with many small base stations deployed, maybe at every traffic signal. Every base station is very small and power efficient, but they are very dense. So CV2X release 14 has a significantly better link budget than 2.11, leading to longer range, up to 2x range. Due to a longer transmission time and waveform and channel coding, so all contributed to 2x longer range. So here's one use case of a disabled vehicle after blind curve. Let's take a 5-minute break and reconvene at 4:01.
I will need to leave now and pick up my kid at the preschool.
Okay.
So if you could leave the recording on so I don't miss the last part.
Yes, I will.
Okay, thank you. See you next time.
See ya. So let's continue on this disabled vehicle example. So here's a scenario. You have a disabled vehicle just around the corner, and it's a non-line of sight. You cannot see it at the straight road section. So, and then V2X will give you a warning. Here is V2V message warning from the disabled vehicle to the oncoming vehicle, to the vehicle behind. So because CV2X has longer range than DSRC 802.11p, the CV2X can get a warning earlier with a longer stopping distance. So stopping distance is estimated as driver reaction time plus braking distance. So the CV2X vehicle can get a warning earlier. Therefore, it can afford to have a larger stopping distance while still avoiding the accident. But for the DSRC equipped vehicle, let me see the figure here. So if it's icy road, if it's traveling at 38 miles per hour with CV2X, it will have stopping distance of 107 meters on the icy road. If it's a normal road, then you can travel at a faster speed. So this versus this. But for DSRC equipped vehicle, the allowed velocity is much smaller, 28 miles per hour on the icy road and 46 miles per hour on a normal road. So this shows that longer range communication results in earlier warning for the vehicle. So do not pass warning. So here's do not pass scenario where you have an oncoming vehicle on the other lane, and it's blocking, the truck is blocking the line of sight of the vehicle here. So CV2X longer range gives the vehicle a higher speed. So the vehicle can travel at 43 kilometers per hour, whereas for shorter range DSRC connection, it can only travel at 28 miles per hour to be safe. So 5G AA is a cross-industry consortium that defines 5G V2X communications. 5G Automotive Association, it's a marriage between automotive industry companies and telecommunications vendors. So 5G accelerates AVs with V2X wireless sensor, CV2X, and DSRC, Wi-Fi, 3D high definition maps, precise positioning with GNSS, heterogeneous connectivity with cellular, 3G up to 5G, Wi-Fi, Bluetooth, a CAN, Ethernet, power line. So these are in-vehicle connection connectivity. Onboard intelligence with heterogeneous computing, onboard machine learning, computer vision, and so on. So they all contribute to autonomous vehicle. So my thoughts are that massive deployment of V2X is necessary for AVs to benefit from V2X. So it's a promising technology, but current AV players are not counting on V2X. All the automotive AV companies like Waymo, Nutonomy, and others, their vehicles do not rely on V2X connections. It's nice to have, but not necessary. So the problem is that if you only have a few vehicles equipped with V2X, especially for V2V, it's not useful. So only when you have mass deployment, then it becomes very helpful, very useful. So right now it's it has some deployment, but people are not counting on it. Okay, so that's the end of the introduction slides. Any questions, discussions?
No, thanks.
Okay, sure. Let's move on to the next chapter. Yeah, someone commented that so much information. So yes, it has a lot of information, but the exam is open book. So what are you worried about? You can always do a quick Control F to find any information. So safety. I'll first have introduction to functional safety and discuss the different steps in the functional safety process, hazard analysis and risk analysis assessment, functional safety concept, techno safety concept, and functional safety for hardware and software. So let's first define our vocabulary. So a fault is when something inappropriate happens to the system, such as a defect or unexpected behavior. A fault can lead to a failure, which is synonymous with a malfunction. So failure means that the system has stopped working properly. I should highlight it. So the system is no longer doing what it's supposed to do. A failure could lead to a hazard. A hazard is a situation that could cause injury to a person or harm a person's health. If the system fails, the situation is potentially hazardous, but not necessarily. So hazards have a different levels of risk. So for example, if a resistor in your car radio hardware breaks, so that's a fault, as a physical defect. The radio will not turn on. That's a failure. That's a malfunction. You won't get to listen to the music, but that won't cause your bodily injury or harm. That won't cause you bodily injury or harm. So it's a hazard with low risk. If a resistor in the power steering hardware breaks, so that's a fault leading to a failure. The power steering could fail. So if you are driving at high speed, then you might get injured quite badly. So it's a hazard with high risk. So functional safety, so it comes from a branch of systems engineering called requirements engineering. So systems engineering separates requirements into functional requirements, what your system is supposed to do. In other words, the system's functions. With the form X, system shall do Y. So for example, the turn signal system shall turn on an indicator light telling the driver that the system is active. Non-functional requirement, how the system should behave. That is how reliable is the system. What with the form X system shall be Y. So for example, the turn signal system shall be available when the vehicle ignition switch is in the on position. So it does not specify the function of the turn signal system, only its availability. Hence, it's not a functional requirement, it's non-functional. So functional safety looks at what happens when the system does something that's not supposed to do, which is called a malfunction. So you will be adding new engineering requirements to the vehicle design in order to ensure safe systems. So automotive functional safety is only concerned with the EE system malfunctions, electrical electronic system. It's just one part of overall vehicle safety. So vehicles have a number of different systems, including EE, hydraulic, mechanical, and chemical. There are a variety of other automotive standards covering topics about safety that do not concern EE systems. So we are discussing EE systems in this course. So functional safety versus nominal performance. So nominal performance issues can lead to safety problems, but nominal performance is not part of the functional safety standard. For example, nominal performance of an automatic braking system could be a vehicle traveling at 60 miles per hour should come to a complete stop within 5 seconds. So functional safety does not determine whether or not the vehicle brakes within 5 seconds. Instead, it will look at malfunctions such as if the braking function is not engaged when it's supposed to, or if the braking function is engaged when it's not supposed to, or if the system brakes too hard, causing injury to the driver. So it does not specify the quantitative performance of the system, like 5-second braking time. So it looks at more qualitative malfunctions. So even though the quantitative metric may be relevant to safety, so if you can not stop within 5 seconds, you may hit a pedestrian, and that's a safety issue, but that's not part of the functional safety standard. So which part of the following is part of the functional safety analysis? One is the mechanical seatbelt restraint system could fail and the passenger would be injured in an accident. 2, testing to see if a backup camera actually meets its technical specifications of a depth perception of 20 feet. 3, there's a potential that a software error could cause the parking brake to engage at high speeds. And 4, a car battery might catch on fire because of a chemical reaction. So normally I would call someone, but since you have the slides, you have the answer. So answer is 3. Parking brake system malfunctions at high speed. So number 1 is not an EE system malfunction. It's a mechanical system malfunction. So it's not part of functional safety analysis. Number 2, it's a performance issue, not a functional safety issue, qualitative performance. Number 4, again, it's a chemical system issue, not a EE system issue. So safety is absence of unreasonable risk. So functional safety analysis is to identify high-risk situations and lower the risk to reasonable levels. It has 3 steps. One is identify hazards in the passenger vehicle's EE system that could cause physical injury or damage to a person's health. One is evaluate the risk of the hazardous situation so that we know how much we need to lower the risk. Last is systems engineering, prevent accidents from occurring by lowering risk to reasonable levels. So we are mainly discussing the first 2 steps in this lesson. So what level of risk is reasonable? So it focuses on keeping the risks below society's current threshold. Let's look at seatbelts, mechanical seatbelts. So it took almost a century for countries to require seatbelt use. Many people consider the Carl to have invented the automobile around 1885. Seatbelts appeared in the 1920s when doctors began installing them on their own vehicles. 1950s, companies offered seatbelts as optional equipment, and end of 1950s, it became a standard equipment. So 1968, United States passed legislation requiring all vehicles to come with safety belts. 1970, Australia followed suit. 1984, New York passed the law, state law to enforce seatbelts. So today, can you imagine purchasing a car with no seatbelts? So by the measure of contemporary society, driving without a seatbelt is an unreasonable risk. In the past, driving without a seatbelt was considered reasonable by society standards. So I use this example to show that the level of risk is depending on the current current years. But for functional safety, it only looks at EE systems, not mechanical devices. So seatbelt is not a part of the functional safety. However, some modern seatbelts contain electrical components. They may be smart seatbelts. I haven't seen one, but maybe there are. Then if it had electronics in it, then it's part of the functional safety. So identify hazards. 3 general causes for accidents. One is human error. So United States National Highway and Transportation Safety Administration estimates that 94% of car accidents in the United States involve human error. Technology error, especially for automated vehicles. So software bugs are a major source of technology error, and human technology interaction error. So when a human and a machine share control of a system, extra care needs to be taken when evaluating safety. So the boundary between what the human is supposed to do and what the machine is supposed to do needs to be clear. Drivers need to understand the warning signals coming from ADAS systems. Interfaces need to make it clear when the vehicle expects us to take over. So some companies like Google or Waymo has argued that low levels of automation are not safe, since it's unrealistic to expect drivers to keep their hands on the steering wheel and be prepared to take over for a long duration of time. So high levels of automation, L4, L5, will remove hazards due to human technology interactions. So I should really say Waymo here. So you've all seen YouTube videos where Tesla drivers play all kinds of tricks to fool the autopilot system that the driver's hands are on the wheel. So autopilot system will issue warning if it does not detect the driver's hand on the wheel for some duration of time. And if it still doesn't detect after some time, it'll just pull over and stop. So some drivers are so confident in autopilot that they hang some kind of object on the steering wheel to fool the autopilot system not to issue a warning, so that he can sleep or play games or do something else, which is very stupid. But that also indicates the hazard due to human technology interaction. For L2 level driving, when the human needs to always have full attention, it's very difficult for most humans to handle, especially for long distance driving. So another quiz, classify the causes for the following. A software bug causes the vehicle to accelerate inadvertently. A driver goes too fast around the curve and falls off the road. A radar-based vehicle detection system is too sensitive and buzzes even when a crash is not imminent. The driver ignores warnings which could lead to an accident if a crash were imminent. So number 1 is technology error. It does not involve the human. Number 2 is human error. Number 3 is human technology interaction error. So in this case, it's too many false positives. It's like it's crying wolf all the time, and human gets desensitized to it and ignores the warning. So and then when the real warning comes, there's an accident. So one important concept is automotive safety integrity level, ASIL. The standard for functional safety is ISO 26262. It defines 4 ASILs, ASILs A to D. ASIL D represents a hazardous situation with the highest risk, whereas ASIL A represents a lower risk. ASIL is a key term in automotive functional safety. There's one more level of risk below ASIL, called ASIL A, called QM, quality managed, which means that development according to accepted quality principles is sufficient to reduce risk. So QM is not covered by ISO 26262, it's covered by another standard, IATF standard. So essentially QM means that the vehicle manufacturer can ensure its quality, manage its quality by itself. There's no need to involve a certification authority. So it's quality managed by the manufacturer. While ASIL determination must be done by a third party certification authority. So ASILs are determined by hazard analysis and risk assessment, HARA. So how to evaluate risk? Risk is probability of occurrence times severity of the harm. So probability of occurrence refers to how often a driving situation occurs. Low for driving on a snowy mountainside, high for city driving. So on the vertical axis is the probability of occurrence. So for the driving on a snowy mountainside is 2. It's not very often for someone who lives in the city, but it's very often for city driving. Severity of the harm refers to how bad the injury is. So if a power steering system malfunctions, it may cause fatal injury for driving on a snowy mountainside, but unlikely for or no injury for city driving. So for mountainside driving, it's 4 for severity. So the risk of power steering malfunction is calculated as 2 times 4 equals 8. It's not very clear here. I should say risk of power steering for driving on a snowy mountainside is 2 times 4. So here are a few questions. Probability of occurrence. Vehicle jump start needed. That's when you run out of battery. Driving in snow, driving at night with no street lamps, driving on the highway. Severity from 1 to 4, and calculate the risks for the following. Driving on the highway, brakes fail at high speed. So driving on the highway, that's probability of occurrence is 4, is very often. And brakes fail at high speed, then it's 4, life-threatening. So that's 4 times 4. And for B, your vehicle requires a jump start. The power steering is not working, but the vehicle is parked on the side of the road and not moving. In this case, it's 1 and 1. Because assuming you are a careful person, it won't be very often. So probability of occurrence is very low, and it's parked, so there's no injury. C, driving in the snow in the city. So driving in snow, 2, probability of occurrence, anti-lock brakes fail while driving at low speed. So you may have some light and moderate injury because you're driving at low speed. So the product is 2 times 2 equals 4. Finally, driving at night on a street with no street lamps. You have 3 as probability of occurrence, and headlamps fail. The severity is light and moderate injury is 2 because it's on a city street, so it's not very fast. So evaluation of the severity may be subjective, of course. So reducing the risk with system engineering. So the system engineering V model has 4 steps: requirements engineering, systems architecture design, and allocating requirements, testing and verification, system integration. The top part of the V represents the entire vehicle as a single system. As you traverse down the left side on the V, you focus on smaller and smaller subsystems. As you go up on the right side of the V, you integrate your subsystems into larger and larger subsystems until you get the final complete vehicle. So on the top left, you start with a bird's eye view of your entire vehicle, and as you move down the left side, you start to split your vehicle into subsystems like climate control, entertainment system, steering system, braking system, and then you define requirements and system architectures for each subsystem. Then you focus on the subsystem like the climate control system and break down the climate control system into its own subsystems like the electronic control unit, the temperature sensor, the fan, the air filter, etc. Each subsystem will have its own design requirements and design architecture. So you can connect the right side of the V and the left side of the V with the arrow. So for every prototype you make or test, you can check back to see if the results match the design specifications. So if the system level prototype matches the system level requirements and the subsystem level prototype matches the subsystem level requirements. So the V cycle is widely used in automotive system engineering. So here's the ISO 26262 standard document. It's a long document with many hundreds of pages, defines the vocabulary and defines each phase of the process. You notice there's really 3 V's, right? A large V and 2 small V's. So we'll discuss this later. Essentially, it's a very long and tedious process of documentation at every step of requirements engineering, requirements traceability, etc. So after listening to this lecture, you can decide if you want to work as an automotive engineer. If you do, like in Volvo, or you are working in the V cycle, then really most of the work is on requirements documentation, and relatively little work is really coding. So here's the V model according to ISO 26262. So first, this standard is compliance is not legally required but highly desirable. So higher up in the V model represents integrated system. So this big basin is the integrated system. And then lower down the V model represents subsystems. That's the 2 small basins. So so the left small basin, this left one, is for hardware development. Right small basin is for software development. So downward arrows on the left side of each basin represent specifying requirements and designing a system architecture. Upward arrows on the right side of each basin represent prototyping, testing, and integration. So yeah, big basin, system level design and development, small basins, hardware and software. So if you flatten the V model, you can see it from a more linear perspective. From This part is the concept phase with requirements engineering from item definition to HIRA to safety concept, and then to the product development phase. You have hardware level and software level development, safety validation, functional safety assessment, release for production, and finally, last step is after the release, you have production, operation, service, and decommissioning. So decommissioning is when the vehicle is too old and should be discarded. So we are mainly covering up to here, the early phases of the concept phase and product development phase. So the development process starts from item definition. You do HIRA, hazard analysis and risk assessment. You get a set of safety goals, and you produce a functional safety concept, which is a set of safety requirements with different ASIL levels. And you map the FSRs to architecture elements, system architecture elements. And then you refine the architecture into lower level architectures like sensors and ECUs, and you refine the functional safety requirements into a technical safety requirement, which is a more detailed, more concrete requirement. And then you map the technical safety requirements onto the architectural elements. So the higher level mapping of a functional safety requirement to architectural elements is more abstract mapping. The lower level mapping from technical safety concept, technical safety requirements to system architecture elements, it's a more concrete mapping. So all these are done before implementation, before writing any code. So let's look at HIRA, hazard analysis and risk assessment. So this is where you brainstorm to imagine hazards where the system malfunctions and causes injury or harm. Then the risk is calculated for each hazardous scenario. So you start from item definition, which vehicle system is under consideration, followed by 5 steps. Situation analysis, choose different driving scenarios like driving on the bumpy road, being towed, and driving on the freeway. Hazard identification, figure out how the system could malfunction. Electronic parking brake might fail. Hazardous event classification according to exposure, severity, and controllability. Combine situations and hazards together, combine these two branches, take a malfunction, and then think about the malfunction under different driving scenarios. So if the electronic parking brake failed while the vehicle was parked on a steep hill, this combination of situation and hazard is dangerous. But if the parking brake fails on a flat ground, and then it's less dangerous. Then calculate 3 metrics called exposure, severity, and controllability, which will depend on the hazard, the driving scenario, and what might happen when the hazard occurs under the scenario. So based on this, exposure, severity, and controllability, you determine the ASIL level based on a table lookup. And then based on the ASIL, you determine a safety goal, which is a type of engineering requirement for vehicle functional safety. For example, the electronic parking brake system shall always be engaged when the vehicle is in park or on a gradient that's greater than 10 degrees. And then after that, you implement the system to realize this safety goal. for example, by writing code to check the gradient and do everything else in the implementation. But up to now, up to safety go, we haven't touched implementation yet. We're just doing requirements. So the terminology of item is a high-level system in the vehicle. A system is a set of elements that have at least a sensor, controller, and an actuator. So we'll discuss this lane keeping system. Has two sensors, a camera sensor and a driver steering torque sensor. So the ECUs are the controllers, and the actuator is the motor that turns the steering wheel. A subsystem is a smaller piece of the system, and a component may be an ECU, an embedded computer that contains the hardware and software for a specific vehicle functionality. A component consists of hardware parts, CPU, GPU, graphics cards, and software units like application, program, memory test, module, and so on. So we look at this running example lane assistance system. So it has two functions: lane departure warning (LDW) and lane keeping assistance (LKA). So if a driver departs a lane without using a turn signal, the system assumes that the driver has become distracted and did not mean to leave the lane. Two things will happen. The LDW function will vibrate the steering wheel to provide the driver haptic feedback. So haptic is touch. So it'll vibrate the steering wheel so that maybe the driver is drowsy and might have fallen asleep. So to wake the driver up. The LKA function will move the steering wheel so that the wheels turn towards the center of the lane in order to stay in eagle lane. So to automatically correct the deviation from the center of the lane. So these requirements, so these two points are requirements that came from a product engineering team. And as a safety engineer, your job will be to add extra requirements to ensure functional safety. I think here is not very clear. So you should say the safety engineers. So I think this is clear to anyone who drives, right? If you drive on the highway, so this can be very helpful for preventing drowsiness. So here's the architecture of the LAS. You have one item, that is the this green box. The whole thing is an item. So the steering wheel itself, the mechanical component, is not a part of the LAS. LAS is only the E system. One system, the red box. So the red box, you can see it's this part. No, it's not very clear. Let me. The red box is this part. So it is a system, whereas the is separate from the car display and car display ECU system for human-machine interaction. So because the red box, the camera sensor ECU, the electronic power steering ECU, these are more tightly integrated together. So it's a more coherent system, but not the car display ECU. and 4 subsystems, the 4 blue boxes. One here. This is one subsystem, another subsystem, another one, and another one within it. So the electronic power steering ECU is a subsystem within the subsystem. So that's the system hierarchy. So situation analysis. This is where people sit around and brainstorm about hypothetical driving situations and analyze what will happen in case of vehicle malfunction. So so for example, this is driving in a mountainous road. You can think of brake failure, control unit short circuit, bit flip, airbag deploys unexpectedly, unintended acceleration, power steering switch shut down, headlamps do not turn on. So yeah, this is all possible malfunctions. To help engineers with this task, it's useful to provide guide words. So predefined guide words. So here you have a bunch of guides where function not activated, function unexpectedly activated, and so on. That's for guide words for malfunction. Hazardous events has another table of guide words, none and front collision with oncoming traffic, and so on, with ahead traffic, with obstacle. So for example, you may have a sentence template like this: operational mode on operational scenario during environmental details with situational details and item usage system. And then you fill in the blanks, fill in the terms in brackets from standard guide word tables. For example, backward driving, operational mode, on city road, operational scenario, during fog, environmental details, with low speed, situational details, and correctly used system, item usage. Or for our example, normal driving on a highway during rain, slippery road with high speed and correctly used system. So, so this is semi-natural language to help engineers better structure the requirements. So hazard identification for LDW. The function is that LDW function shall apply an oscillating steering torque to provide the driver haptic feedback. Malfunction is when actual effect is too much. That is, the details are the LDW function applies an oscillating torque with very high torque above limit. Then it may collide with other vehicle as the hazardous event, because the high haptic feedback can affect driver's ability to steer as intended. The driver could lose control of the vehicle and collide with another vehicle or with road infrastructure because the steering wheel is vibrating too violently. So summary description is that LDW function applies too much an oscillating torque to the steering wheel above limit. So for the LKA function, a lane keeping assist function, it will move the steering wheel so that the wheels turn towards the center of the lane. So the malfunction is that the driver takes both hands off the wheel. The detail is that the driver misuses the function by taking both hands off the wheel and incorrectly treating the car as an AV, causing LKA function to be always activated. The hazardous event is that collision with other vehicle is possible. So event details, summary description are omitted in here. So this is a human machine interaction error. Well, the previous one is also a human-machine interaction error. So if the LKA function works too well, driver may be tempted to just relax and take the hands off the steering wheel, like the Uber, like the Tesla owners, and then it may cause a collision. So ISO 262 defines the risk as severity times exposure times controllability. So we discussed risk before as probability of occurrence times severity of harm. So there's actually a family of different standards for safety certification in different domains. There's the IEC standard for industrial automation that is in factories. There's other standards for power grids and so on. So they're all similar. The concepts are all similar, but details differ. So this particular risk definition is specific to ISO 26262, whereas the previous risk definition is generic for many standards. So severity is the same. Its exposure corresponds to a probability of occurrence. It just has a different name. Controllability measures how likely driver could gain control of the vehicle. So probability of loss is computed as exposure times controllability, and risk is based on the previous formula. You get the next formula. So severity times probability of occurrence, which is equal to exposure times controllability. So you have these tables for determining severity, exposure, and controllability. Severity is defined from S0 to S3. Larger numbers indicate more severe consequences. AIS, accident injury scale, for determining severity. So I have some notes below is provided by the Association for Advancement of Automotive Medicine. A0 is no injury, A1 is light injuries, up to A6, AIS6, which is critical injury or fatal injuries. Next table is for exposure. Incredible probability or very low probability or high probability. For example, driving in the city is high probability E4, and driving on a snowy mountainside is perhaps E2 with low probability. Last table is for controllability. That is, can you control the vehicle if the function fails, malfunctions? From controllable to up to difficult to control or uncontrollable. So less than 90% or more of all drivers or other traffic participants are usually able or barely able to avoid harm. That's C3. So let's look at one example. Normal driving on a highway during rain, slippery road with high speed and correctly used system. So severity is S3, life-threatening or fatal injuries, because it's highway driving. So look at S3. More than 10% probability of AIS 5 to 6. So that's life-threatening injuries. So I'm sorry, let's wait for which system? Let me see. Lane keeping, lane assist system. Yeah. So yeah, it's S3. Exposure is E3, medium probability. Situation is not uncommon, but also not every day. So E3, it says here, 1 to 10% of average operating time occurs once a month or more often for an average driver. It's E3 okay for some place with sunny weather, but for some place like London, where it rains half the year, then it's probably with higher probability. Controllability is C3, difficult to control or uncontrollable. So if the steering wheel vibration is excessive, then driver may lose control. So based on these three metrics, we can determine the ASIL level at ASIL-C. So S3, this column, E3 and C3. So C3, E3. Look up the table, you have ASIL-C. Okay, I think I should stop here today. We'll continue next time. Any questions or discussions?
Well, for all these standards, I mean, usually in traditional study environment, we might discuss things together as students, and we might be able to clarify things for each other. But now with this distant learning study mode, it seems difficult to communicate with someone where we can discuss about these sophisticated concepts and clarify them for ourselves. I mean, there are a lot of things in this subject to learn. Some of them are technological, some of them about like legal or emergency concepts. So I mean,
yes,
yeah.
I see your point. It is a very comprehensive course that covers many touches on different topics. So there's a discussion board on Canvas, but it's obviously a message board, not real, discussion room. Yeah, I very much welcome any posts in here, so we can have discussions. So I guess I think Zoom has a function of dividing up the class into discussion groups, but I don't know how well it works. It may be confusing to many students. So yeah, so I understand that the material is a little bit overwhelming. So that's why I often give a review of previous class material in the next class, just to to give you a chance to discuss.
To tell you the truth, Mr. Gu, a few days ago I was going through the lecture material. There are a lot of concepts. Every system is divided to many subsystems. For example, when we were reading about the supervisor, about the hierarchy of the system, which overlooks the localization, about checking the environment around, about mapping and other stuff. Although I can see the great job you did in detailing the information as much as possible, but still many of these subsystems are very difficult to understand on your own.
Oh, yes. Did you mean this picture?
Yes, sir. Yes. And you were describing in detail about the controller, about the system supervisor, motion planning. Every one of those blocks, there was a further explanation on it on the upcoming slides to come later. And it's too much of information to glue and to interconnect with each other and to understand how do they work for thoroughly. It's quite challenging. I mean, I can see from the comments of some of my colleagues that they do feel that the information is quite overwhelming in its quantity and its depth. But I still like the way you put the slides because they do describe a lot. It's a very difficult subject to teach, but I mean, is there a kind of questionnaire that would come with every lecture note in, to examine how much you understand of the subject?
Yeah, I was thinking of giving out a few quizzes during the semester, but I'm caught up in the deadline until April 7th. So after that, I may have more time to prepare a few quizzes.
Okay, are there any old exam papers that the student would just give a look? He might feel that they are relative to the first lecture, to the second lecture, and then we would know what to concentrate on, really.
No, because it's my first time teaching the course. Actually, I'm still working on the slides for the subsequent lectures. That's why I only uploaded 3 chapters up to now. So I'm still working on everything else. And yeah, but before the exam, I will definitely give out a set of sample questions so that you have better idea of what's going to be covered.
I mean, for example, the mission planner, is this like a depth first kind of search?
A depth first is one possibility. You have dexterous algorithms and A-star search, which are more often used. I will discuss this later.
To tell you the truth, I took this subject at Introduction to Artificial Intelligence, but it wasn't one of the subjects that I understood well. I mean, I tried to understand as much as possible to pass the exam, but it would be really great if we could have a better explanation of such parts of the lecture of this lecture, like how the way search is being done, and also the behavior planner. I was a little bit confused with that. Yes, sir, this one. Because I couldn't. It seems that you could jump from a state to another, to deaccelerate to stop, and then to stop fine, and then deaccelerate to stop to track speed. What is meant by track speed? I mean, normal speed of driving.
Yeah, just to set a speed like 60 miles per hour and just track that.
So how it comes that I would be deaccelerating to stop and suddenly I would go into track speed? Why would that happen? I mean, I would understand logically deaccelerating to stop and then coming into stopping condition. And after stopping, I would accelerate again into a track speed. But from deacceleration to stop directly into track speed, why would I do that?
I think that's possible because you may see a red light in front and you're trying to stop and then the light turns green and you just go ahead, right? So you don't have to stop.
Okay. And what is meant by follow leader, sir?
It means that your leading vehicle is blocking your way. So you have to follow its speed. You cannot track your own speed.
If somebody in front of me and he's going with a certain speed, then I should take a speed similar to him
Yes.
rather than.
It's like adaptive cruise control, right?
But I think on let's say a highway, although you are advised to have a relatively high speed, but you are allowed to have your own speed as long as I mean, on highway, maybe there isn't really a high speed, or maybe it's 100 kilometers per hour or something like that. But you can drive less. Legally, you are allowed to drive less.
Yeah, of course. So what is your question?
My question is, why should I follow a leading car if I have the freedom to drive on a lesser speed? I mean, from the legal point of view, there are usually maximum speed that you should not exceed. If you are on a highway, you are advised to drive with a relatively high speed, but there isn't really how can I say it? An enforced speed on a highway.
Oh, yeah.
Yeah.
So I can give you a few scenarios. One is perhaps you're following the leading vehicle who is your friend. You're going to a picnic, right? You need to follow this car. Another may be that you're driving on a two-lane road where or a single-lane road. There's no passing in this particular segment, so you have to follow the previous car. You cannot pass it.
Okay.
Yeah.
Okay. That clears it then. Okay.
Okay. Yeah, so regarding your comments on the contents of the course, it is very quite diverse. So I thought of covering reinforcement learning. If you talk about learning-based approaches, it's actually simple from some perspective because you just train the neural network to do everything, right? But if you're talking about classic pipeline, every box is a single algorithm, and you can devote a course to every single box in this picture. So it really depends on how much you want to cover for each part. So for me, I try to focus more on the motion planning and controller part. For the perception, because there are already courses on deep learning on computer vision, I try not to cover that too much. And also for the latter part of the course, reinforcement learning is also focused on planning and control because perception is a separate part in the reinforcement learning pipeline. So I have some preferences for different parts of the pipeline, but I will try to keep the material self-contained. That is, I will try to keep the background knowledge to a minimum and introduce the concept from scratch. Okay, so if there's any further questions, just leave messages on the board. And or just send me message, send me email. Let me see if there's anything on the chat. No. Okay. So if there's no more questions,
Can you hear me?
Alan?
Yes.
Yes.
Okay. I want to check just if my microphone was okay. But I'd like to have some more material about, especially about reinforcement learning.
Yes. So reinforcement learning will be covered. So starting from week 5.
Okay.
So the reason is that reinforcement learning is really a research approach where industry mainly focuses on the classic pipeline. Even for reinforcement learning, it's often used to replace part of the pipeline. So it's a hybrid approach typically, not a full end-to-end learning. So to make it more relevant to industry, I try to cover also the classic pipeline.
Okay.
Yeah. Any more questions? Okay, so have a good evening. Class dismissed.
Thank you very much.
Yes.
Thank you.
Bye-bye. Yes.